Let's talk about double angle formulas. Okay, so this is another identity that's on your formula sheet for this chapter. And here they are. Sine of 2 theta equals 2 sine theta cosine theta. Cosine of 2 theta equals, there's 3 different ways that we can represent that. Cosine squared minus sine squared, 1 minus 2 sine squared, 2 cosine squared minus 1. Tangent of 2 theta is this ratio. Okay, so let's just briefly look where these come from. So cosine of theta plus theta equals this minus this. Okay, this is from the sum and difference formulas that we did in the last section. Okay, so this is just that equation if our two angles are the same, if they're both theta. Okay, so we can write that as cosine squared minus sine squared. We can write cosine squared using the Pythagorean identity as 1 minus sine squared, where we get this third one. Okay, so sometimes it depends on the problem. Each of these 3 representations might be useful. They're all on your equation sheet. Again, from sum and difference formulas, sine of theta plus theta is this, sine of theta times cosine of theta plus cosine theta sine theta, which is just this representation, 2 sine theta cosine theta. And for tangent of, so here's the sum or difference for tangent of theta plus theta. We plug these in, we get 2 tan theta minus 1 over tan squared theta. Okay, so these are all directly from the sum and difference formulas that we used last time. All right, so let's do some examples using these formulas. All right, so given that tangent of theta is negative, let's see if you can see this, negative 3/4, and theta is in quadrant 2, find the following. All right, so it looks like we're going to have to draw a triangle, right? Here's our triangle, here's our theta. Tan of theta is negative 3/4. We're not going to worry about the negative sign until the end. And so this is a 3, 4, 5 triangle, or we could use a Pythagorean identity, right? So I might just write this out. We know that sine of theta is going to be 3/5, and in quadrant 2, sine is positive, right? So this is going to be positive 3/5. Cosine of theta is 4/5 adjacent over hypotenuse, and in quadrant 2, cosine is negative. And they tell us that tangent of theta equals negative 3/4. You don't have to write these out, but it's, since we're going to have 3 sections, 3 parts here, might be useful. So sine of 2 theta. So have we figured out what theta is? Nope. We don't care what theta is. Okay. We just want to find what sine of 2 theta or cosine of 2 theta or tan of 2 theta. So let's look up here. Sine of 2 theta is 2 sine of theta cosine of theta. So it's just going to be 2 times 3/5 times negative 4/5. So I don't know, what is this? Negative 24/25. Not too tough, especially if we write it out at the first. Helps us not make mistakes. All right, so cosine of 2 theta. Let's go up here. We've got different options. I don't know which of these will be easier. Maybe let's do this one. 2 times cosine of theta, so negative 4/5 squared, minus 1. So that's going to be 2 times 16/25 minus 1. So 32/25 minus 25/25 gives us 7/25. Okay. And lastly, tan of 2 theta is going to be, so 2 times tan of theta over 1 minus tan of theta squared. So negative 6/8 divided by 1 minus 9/16. So negative 6/8. This is going to be 7/16. So negative 6/8 times 16/7, negative 12/7. Okay, so nothing too fancy here, right? The key is using the information they gave us, the fact that they told us that tan of theta was negative 3/4, we drew our triangle, we figured out our other trig identities, or trig ratios, and then we're just plugging into the equation, okay? Let's do another example. Use the double angle formula for cosine to write cosine of 6x in terms of cosine of 3x. Okay, so they're giving us a clue here. They want us to use the double angle formula, so I'm going to write it like this. Cosine of 6x is cosine of 2 times 3x, right? And if we go back here, and they want us to be in terms of cosine of 3x, is that right? In terms of cosine of 3x, yes. Okay, so we have three options here for cosine of 2 theta. We could write it this way, or this way. They want it all in terms of cosine, so I'm going to choose this third representation. It's going to be cosine of 3x, cosine squared of 3x minus 1. That's it. Done. Okay, we've written this in terms of cosine of 3x, right? If we know what cosine of 3x was, we could plug that in, but we don't, right? This is just what the question asked us to do. Okay. All right, what about example 3? Establish the following identity using double angle formulas. They want us to show that 1 plus sine of 2 theta equals sine theta plus cosine theta, this whole thing squared. Okay, so we'll go to our equations. And let's see, sine of 2 theta is this. So let's write that. 1 plus 2 sine theta cosine theta. I'm just replacing this with that equation. All right, maybe we need to multiply this out. Let's see if things cancel. So let's see if we can use a generic rectangle, we can FOIL. We're going to get sine squared theta plus 2 sine theta cosine theta plus cosine squared theta. All right, if we multiply that out. All right, well, what do I see? Sine squared plus cosine squared equals 1 by the Pythagorean identity, right? Sine squared plus cosine squared equals 1 plus 2 sine theta cosine theta. Got it. That's what they asked us to verify. Right? Original problem said to verify that this equaled that. So we used the formula given to us to replace this sine of 2 theta with this. We FOILed this out. We used the Pythagorean identity, and we saw that they were equal. So a lot of times, that's another thing that happens a lot of times verifying these identities is you work a little bit on one side and a little bit on the other, and then it shows that they're equal. All right, let's do one last question here. Let's verify this identity. Tangent of 2 theta equals 2 over cotangent theta minus tan theta. All right, so I'm going to break the rule that I've been telling you. I've often been saying, work with the more difficult, more complicated side first, right? Which in this case looks like this for sure. However, here we've got this tan 2 theta. That's something I have an equation for, right? What if I just said, okay, on the left side, I'm going to use my double angle formula and just say this is 2 tan theta divided by 1 minus tan squared theta. Right, I've just replaced the left side with that equation. Okay, I want it to look like this. How could I make this look like that? Well, I'm noticing I've got this tan here, and I just want this to be a 2, not have that tangent there. So what if I multiply all the terms, the top and bottom, by 1 over tangent? Let's see what happens. Because I'm trying to get rid of this tan. So 2 tan theta divided by tan theta divided by 1 minus tan squared theta divided by tan theta. See what I did there? I multiplied the top and bottom by 1 over tan theta. I had the idea to do that because I noticed this is what I want it to look like. This is also very helpful in verifying identities. Try to look at where am I going? I'm trying to get here, and I'm here. So I want to get rid of this tan. So that gave me the idea to try this. Let's divide the top and bottom by tan theta. So what's going to happen? I'm going to get 2 here, and I'm going to divide this into each of these terms. I'm going to get 1 over tan theta minus tan theta. Well, what is 1 over tan theta? I'm trying to get here, and yeah, great. 1 over tan theta is cotangent theta. And I got there. Okay, so I had 2 big ideas here. The first was to use my double angle theorem. The second was to divide top and bottom by tangent, because I saw here's where I'm trying to go, and I've got this tangent in the way. So I'm going to get rid of it by dividing top and bottom by tangent of theta. Okay, so those are the kinds of problems that you can solve using the double angle equations. Good luck.